All right, so in this question, we want to evaluate the gravitational potential energy in between two 9 kilogram spherical steel balls separated by a distance of 22 centimeters. And then, assuming that they're both initially at rest relative to each other, we'll use conservation of energy to find how fast they're traveling upon impact. So, two equations that are going to be important to us here are the equation for gravitational potential energy. And notice we're not using the one that's MGH. That one is used more so if we have something like an object that is relatively close to Earth's surface, or another planet's surface, and we know what the little g is, which is the acceleration due to gravity due to one of those objects, but we don't know what that is here. So we have to use kind of the more like standard version of this equation. So that's this one, and our equation for kinetic energy. So to start, just to evaluate the gravitational potential energy between them, we're going to use that equation and just plug in those numbers here. So big G is our gravitational constant, 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared. We have 9 kilograms for both of those masses. And then the distance between them, we're going to just change that into meters. So that would be 0.22 meters. And we come up with our answer there. So let's see what we get. We get 6.67 times 10 to the negative 11th times 9 times 9 divided by 0.22. So that is negative 2.46 times 10 to the negative 8th joules. So that's the first part of our problem. In the second part, we need to use the work energy theorem to see basically what's going to happen is here as these objects move closer together, they lose gravitational potential energy to gain kinetic energy, because as they get closer and closer together, their speed is going to be increasing. So kinetic energy goes up as gravitational potential energy goes down. So if we look at the equation related to the work energy theorem, which also is going to help us out with this idea of energy conservation, we're going to think of the initial state as these objects being that further distance apart, where our initial is 0.22 meters. And then the final state will be right when they make contact with each other. And that distance then that they'll be apart would be equal to the sum of their radii. So if the radius is 0.055 meters, we're going to double that to get that final distance. And we can simplify this equation a little bit. We don't have all of those types of energies in the initial and final state. We don't have work done. We don't have any initial kinetic energy because the initial kinetic energy is zero. There's no speed at first. We do have initial gravitational potential energy, no elastic potential energy, no work done by external forces. We do have final kinetic energy. We do have final gravitational potential energy, but nothing going on with springs. So we're going to leave anything with elastic potential energy out. So to solve for part B, we're going to use that simplified equation. So we have UG initial, kinetic final, gravitational potential final, and we can substitute in the equations for each of those things and then the numbers. So for that initial gravitational potential energy, G m1, m2 over the initial distance. For kinetic energy, we have 1/2 mass times that final velocity squared. That's what we're going to be solving for, is that final velocity. And then this expression, again, for that gravitational potential energy, but for that final distance. So we have the masses. We know that G is that constant. We know what those distances are. And with the mass here, we notice like there's only one mass. So which mass is it? Whichever mass, and it doesn't matter in this case because their masses are the same. We're just going to use 9 kilograms there, but in general, we would just be using this equation to find the speed of like whichever object we're trying to find the speed for, that's the object whose mass would go in that location. So we can actually cancel mass out, not all the masses, but we could cancel one of these in each expression to solve for that final velocity.